Man, it's kind of cool that this is the only low-level thing you need in here, which means that it's going to be easier to port that to other platforms. So the less the contact surface area with actual CPU, the easier it is to then port to ARM, for instance. Because on ARM, you just need to implement these things. And there you go, you support ARM. On another platform, you just implement these two things, and they're very simple. I'm pretty sure on all of these CPUs, it's going to be pretty much the same. It's just like the registers are going to be different, and instructions maybe going to be slightly different. And even if we want to compile on something like MSVC, it's really easy to if-def all of that stuff, right? So it's a very small compiler and platform dependent part that is very much like easy to port. I'm super happy with this implementation, actually. I didn't expect it's going to be this good. Hello everyone, and welcome to yet another recreational programming session with Mr. Zozin. So we have this interesting library which implements coroutines. Right, for those who don't know, coroutines is a really cool concept. Right, so essentially imagine that you have a procedure, right, which counts from 0 to 1, right. So, and essentially, if you just call this procedure as is, it will print from 0 to 9, right. Nothing particularly special. Nothing particularly special. Look at that. So, when you try to call it twice, obviously you're gonna get from 0 to 9, and then you're gonna get again from 0 to 9 because you call them sequentially. So what if you want to actually execute them in sort of like a parallel? You can actually spawn two threads, right? But what if you are in a single-threaded environment, right? So what if you're in a single-threaded environment, though you still want to, execute these procedures or logic those procedures execute, sort of in parallel, switching between them. To simulate sort of like multi-threading. It's kind of similar to how earlier operating systems did that, right? So with a single CPU, with a single core, right? So if you had a single CPU, single core, like a Windows like 95, for instance, would still appear, parallel, right? So what they would do, they would actually switch between the processes, right? So periodically they would send some sort of an interrupt that interrupts the process, and then operating system switches to a different process and then to another process, and just basically round robins between them, but not necessarily round robins, right? So they maybe have some sort of a fancy strategy to schedule the processes and stuff like that. What if you want to do something like that, but within like a single process? Well, this is where coroutines come and play, right? So essentially, there is this yield operation, a really interesting yield operation that allows you to basically switch to another routine. Right, so essentially, if you're running several core routines simultaneously, routines may say, okay, so I'm done for now, let the other coroutines do their thing. And then you can come back to that, it will do a little bit of work, and then switch to another one. So, and we implemented a library that does that, right? So you first have to initialize it, then you say, okay, spawn these two coroutines. And what we're doing indefinitely, we are essentially yielding, basically switching to the next coroutine. So when you do yield, it will switch to one counter, do a little bit of work, then yield again, switch to another counter. That counter will do a little bit of work, then yield again. It will yield to the main coroutine, which will yield again to another counter, and they're going to be basically interleaved, right? So they're going to be basically interleaved, and if you try to run this entire thing, as you can see, this is exactly what happened. We have 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and we're basically like a round robin between these coroutines. We implemented that. We implemented it entirely in assembly, right? So here's the implementation in assembly. It's implemented in FASM. The way it is implemented is that every time you create a coroutine, we allocate a new stack, a new buffer for storing some of the registers. So, and essentially when we do yield, what we do is that we look, okay, so what's the next coroutine? We switch to that next coroutine, switch in the stack, switch in the register, and continue execution until the next yield, and that's how we round robin between them. So that's basically what we have in here. And I need this library because I want to add asynchronicity to my WebSocket library implemented in C3. Right, so I have it somewhere here. So yeah, I was thinking what kind of sort of like a synchronous model I want to use for this specific library. So you can actually find this library in here. and I'm going to actually put it in here as well. One of the asynchronous models that I wanted to use initially is futures. I even implemented like a small future library in C3 as well. But the problem with using future is that it's a completely different computational model from like just a regular imperative code, which means that I will have to rewrite basically 90% of my WebSocket code. Then some time ago, I actually discovered a really interesting library, libmil, right? So which implements like a sort of coroutines Go style, right? You can find it in here. I can't really open it because of my internet provider and stuff like that. And I got really fucking inspired because this kind of like a style coroutines will enable me to actually not rewrite majority of my code, right? So I'll probably add a little bit of code, like a little bit of boilerplate to initialize coroutines and stuff like that, but the code that implements the logic is probably going to stay the same, right? And so yeah, that's what I'm doing right now. I'm trying to implement my own coroutines library, and that's what we're going to be doing today. We're going to continue developing this thing. The problem with this library as of right now is that it's written in assembly, right? So the reason why I was writing it in assembly is because I want to minimize the amount of noise introduced by the compiler, right? So because compiler introduces a lot of uncertainty, it just like shuffles around the register. When you insert inline assembly, you don't really know exactly what is your assembly environment, right? So because again, compiler kind of introduces a lot of noise. So to reduce the amount of noise, I decided to take control completely over the computational environment and implemented everything in assembly. But the problem with assembly is that I started to want to do a lot of complex logic, right? So because I need to manage data structures to store the context of the coroutines, right, and switching between them, between the context and stuff like that. And it's really painful to do in assembly, even though I have a lot of control over how I capture the environment and how I observe the environment and stuff like that. I still just want to have like a little bit more convenient modern language to work with. So, and I decided that the time has come to actually rewrite this entire thing in C, right? And another problem with this assembly is that it's written in a very non-relocatable way, right? So which actually makes, I think, like linking very painful to the point that we have to do these kind of weird little tricks, right? So I have no idea how it even works, but essentially if I just try to maybe use something else, right? If I just try to link things as is, without anything special, I think it's not going to even compile. Yeah, so we may try to do maybe something like this, right, and link them as this, and yeah, so things are not relocatable, and since the library is implemented in assembly, I have to manually rewrite this thing to be more relocatable, and I'd rather do all of that in a higher level language, right? So you can compile just with no PIE. Well, I mean, it's up to assembly, right? So we already spent too much time on the previous stream figuring out how to freaking compile this entire thing. You really want to keep pushing that into this path? You really want to keep pushing this path, even though we already reached the point of shit ton of different flags, and you really want to go there. I don't want to go there. You may want to go there. So the code is open, but I want to actually do something better, something that is easier to maintain, right? So if you like to waste your time, go ahead. The code is open. I'm not going to be wasting time. So right, how are we going to be doing all of that? I think the only reason why we need assembly is because we want to capture a little bit of a, like the current environment, and specifically the current stack, to be honest, right? So the current stack is more than enough for us. So we also need to capture a bunch of registers, right? So specifically, if we take a look at, you know, long jumps implemented in Musel. So let me actually see. Long jumps implemented in Musel. I think they are somewhere in third party. So here is the Musel, and I want to find the file with the path that contains things as x86-64 set jump, right? So set jump basically saves the current environment, right? So let's actually find this entire thing. So here's the stuff. So it saves a bunch of registers in here. So as you can see, it saves RBX, RBP, R12, R13, R14, R15, and so on and so forth. It also saves like a bunch of stuff about the stack, which I don't really know what's up with that. Right, so we also need, on top of saving the pointer to the top of the stack, we also need to save these kind of registers. So I don't know what exactly the registers we have to save, and I don't know the justification of why Musel and also glibc saves these specific registers. Maybe there's something about the Linux API or how the compilers, C compilers usually work, but I'm gonna just like blindly believe that this is the registers that we need to properly save the computational environment, and we're gonna save the same registers. Right, so when we're talking about setJump usually saves them in a parameter, right? RDI usually contains the parameter that is passed to setJump, right? So if we take a look at this setJump, maybe I can even take a look at the, you know, this thing in here. So man page didn't really work properly. setJump. Can you just give me setJump, please? Where is setJump? So maybe this one. There we go. So here's the parameter, and it accepts jump buffer, which is an opaque pointer to the buffer, right? And and it just saves all of these registers into that buffer. In our case, since each individual coroutine has its own stack, maybe one of the things we can do, and this is rather interesting, is to save all of these registers on the stack, and then you know, use the top of the stack as the environment that we kind of saved, right? So that way, the entirety of the context is just like one single pointer, right? And you just switch between the pointer, right? You just switch between the pointers, and the top of the stack usually just contains, you know, the all of the registers and stuff like that. So I think that's a pretty cool idea. I think that's a pretty cool idea. Chat. So I'll get some subs. We'll get some subs. I think I need to acknowledge them. So who was the last? Doruk Sega, thank you so much for trying with the message. 10 months. Yo. Belisarit, thank you so much for tier 1. Kwakislav, thank you so much for tier 1. With the message, tabs design compiling is slacking. It is. It is in fact slacky working. All right, so let's go to the coroutines and let's actually try to think a little bit. So I want to maybe create something like a coroutine new ASM, right? So this is basically what we have, and we're going to have a format elf64, right? elf64. So essentially, how we're going to be doing all of that? So if I want to implement everything in C, right, I want to implement everything in C. So let me, I don't ever know. I need to come up with like a better name. So this is new, and let's maybe call this main new C as well, right? So I think I want to start with yield, right? So I want to have some sort of operation coroutine yield. There we go. And yield basically switches to the next coroutine. It basically switches to the next coroutine. So here's going to be the entry point and stuff like that. The thing about yield is that it needs to take its own stack, right? It needs to take its own stack. One of the things we probably could do is to use some sort of like an inline assembly, right? And maybe just like grab RSP and save it to one of the registers. But the problem is usually these kind of procedures, they have some sort of like a prelude and epilogue, right? So they usually push the base pointer, maybe shuffle things around, allocate some things and stuff like that. So maybe if we have some variables in here, so the RSP is not going to be pointing at the return address of the yield, and return address of the yield is actually kind of important. It is actually kind of important. If we go down, so there is something like attribute naked. I don't really want to depend on like GCC extensions too much, honestly, right? So I don't want to really depend on GCC extensions too much. We could do something like naked. Yeah, maybe, yeah. So it's not really that difficult to then later, you know, get rid of all of that. But I think I want to do assembly completely in FASM. So naked is just using gas then, I suppose, right? So you're just like going down to gas. But anyway, don't really want to go into that route. Honestly, don't really want to go. I don't really like gas and GNU assembly and AT&T assembly and stuff like that. I don't really feel comfortable working with this really weird syntax. So what we can do a little bit of a trickeroony, right? A little bit of a trickeroony. So as I said, the return address of yield is actually kind of important, right? So because the return address of yield points at the address after the call to the function, right? That's what it is. So because essentially, if you have instructions in the memory, so you have something like call, and then you have some other next instructions. So you have RIP, which is the register with, what is it called, instruction pointer. So, and usually what happens, right? So what it does, it first loads the call instruction, right? It reads the call instruction, so RIP now points at the instruction after the call, right? And only after reading the call instruction, what it does on the stack, right? So on the stack, it actually pushes that current RIP as the return address, and only then sets the RIP to the address of the function that you called. So at the top of the stack, you have that RIP after the call. So when you return, you actually return to the thing after the call. So in for yield, that return address being on the top of the stack is kind of important for us because we're going to be using that specific return address to save the environment. Because when we're switching back to the coroutine that called that yield, we're going to be jumping to that address after the yield, sort of restoring the execution. You see what I'm talking about? Does it make sense? I hope it does make sense, right? So, and it's roughly what set jump is doing. In fact, I stole that idea, that trick from set jump, right? So, because this is what it was doing. So save return address pointer for a new RIP, right? So it basically takes a look at RSP, literally like at the top of the RSP, and saves the top of the RSP into this register, and then from this register into the RDI, which contains the pointer to the buffer, right? So it really literally takes that return address from the top of the stack and it just saves it. So then later it's going to jump back to it, right? So it's going to jump back to it. And because of that, it's kind of like important, super important for us, in my opinion. So we could do some sort of a naked thing in here, but I don't want to deal with the gas or anything like that. I want to work with FUSM. So let's go to maybe new coroutine, and let's introduce something like a coroutine yield. So let's actually use assembly not as like a low layer, I would even say, but more as a wrapper around C code. This is a rather interesting idea, like as a wrapper around C code. Because as soon as you call this thing, right, so this is basically a naked function, right? So it is basically a naked function. And you know for a fact that, yeah, our RSP contains the return address. And essentially what we can do in here, we can move RSP into RDI, which is the argument of this entire thing. Right, and then we can just like jump to a C function, right? We're jumping to the C function, not calling the C function, by the way, but jumping into the C function, right? So because jumping into the C function will make it look like when you called coroutine yield, you actually called that wrapped function, right? And because it preserved the return address, it's going to return correctly and stuff like that. But I mean, in case of a yield, it's probably not going to return, right? So I don't think it is going to return. As I'm wrapping C code, we've done full circle, yeah. I mean, why not? Why not? I think it makes sense, right? So how are we going to call this entire thing? I suppose we can call it, I don't know, so something like switch context, coroutine switch context, right? So in a switch context is actually going to accept the pointer to RP. Actually RSP, right? So it's not RP, it's RSP. So we're taking RSP and we're saving it in here and we're jumping it in here, and we should be able to actually have it in here. We can even try to do something like this. Maybe so RSP is equal to P. RSP. So I think you're doing something like register int fasm rax to save. Like again, like I need to learn all of these GCC magical tricks and stuff like that. Like I don't know them. I don't want to use them. Right? It's just like. Anyways. So I have like a very simple FASM assembly, and I have like a standard C, right? So, and yeah, that's it. Like, why do you need like the magical GCC stuff that just like nobody freaking knows about? And like, fuck that. Right. So what do we have in here? Yeah, people really want me to use the GNU shit. I have no idea why. Are you guys all fans of GNU? Like, I don't fucking understand. Like, I fucking hate GNU, right? So it's just like, it makes everything overcomplicated. Honestly, GNU, like, code of GNU is as cancerous as Microsoft. I think they are competing with Microsoft in cancerousness, in all fairness. Well, I mean, so the way to beat cancer is to become cancer, apparently. I don't fucking know, right? So it's just like more obnoxious cancer. Honestly, like sometimes GNU does use a lot of the Microsoft tricks in terms of like, you know, embrace, extend and stuff like that. Just saying. Right. So, but also, you know, defending themselves with sort of like a higher moral ground, right? So you can't criticize GNU. How dare you criticize GNU? Anyway. So we got some subs. Thank you so much, Simeon, with the Twitch Prime. Thank you with the message. Thank you for the recreation programming project. There's so little no BS software engineering content on the web, and it always makes me happy when I see your stream notifications. Much respect. Thank you so much. Not Flatline. Thank you so much for Twitch Prime. Thank you. Anyways, so let me see what is going to happen. So. We're doing yield, and I suppose I'm going to say that yield is going to be this sort of function, right? So we're just yielding. I need to rebuild the whole thing. So here we're going to be doing the new stuff, right? So this is the new, this is the new, this is the new. And for the main new C depends on the new coroutines, and we're going to do in GCC. Oh! So, and let's actually do main new. Okay, so we didn't like something. Yeah, so we never actually declared this thing. If I remember correctly, it is something like extern or yeah, I have no idea why. Like, so it's just like fuck that specific letter. Like, why not just extern? Right, so that's what it is. All right. Okay, so implicit declaration of printf, not that big of a deal. So std ayo. Okay, so and it now tries to call to coroutine yield. Didn't I define? I think I also have to declare this thing public. Yeah, there we go. So that seems to be working. And now, if I try to call this entire thing. That seems to be the, yeah, that looks like an address to the stack, right? That really looks like address of the stack. And because, look at that, because we jumped into the C function, the return address stayed intact. So when the coroutine switch returned, it actually returned from the return address of the coroutine yield. So it's a very kind of like a thin wrapper around C function that just captures the current environment at low level and forwards it to the C code in a very thin, straightforward way. This is actually kind of cool if you think about it. It's actually kind of cool. So just forward it there. So, and if we used, you know, naked C functions, it would be pretty much this, right? Wouldn't it? I think it would be pretty much this, right? Just like to capture a little bit of environment and just like forward it to switch context, right? Okay, so, and when we switch in the context. So, and by the way, in the previous version of the coroutine, we were allocating these stacks and structures and stuff like that we can now allocate all of that shit in C in a more convenient manner, honestly. We can even use dynamic arrays. Imagine using dynamic arrays from C. I mean, it's doable, but it's kind of painful, right? So you have to do a little bit of a lubrication, but why if you can just use C? Right, so let's go ahead and just like do C. So we can introduce some structures, right? So I don't know, so struct context, right? So this is going to be context, and in the context we can actually store the RSP and some sort of registers, right? So, but I suppose registers, the register that we want to store are going to be stored on the stack, right? So if I take a look at the new OASM, right, so before going anywhere, before actually forwarding this stuff into the switch context, I think we need to push all of the necessary registers on the stack. STBDS goes brrr. We can try to use STBDS, so at some point. But honestly, like, I don't think we need hash tables right now. Maybe dynamic arrays are going to be sufficient. STBDS, as far as I know, also contains dynamic arrays, but I have my own dynamic arrays that are much more simpler. Yeah, we can now have more than 10 coroutines, exactly. Because one of the limitations of that library was that how many coroutines we could have? Right, so we could have the capacity, which is 10. I mean, I could always recompile it and give it more than 10, but I mean, it's just like, it's not dynamic, right? It's hard-coded. So we can actually unhard-code this entire thing. Okay, so we got some more subs. Thank you so much, Leicho, for 2 months with the message. Do you get the money from subs or no? I do not get any money from subs. Or should I move somewhere else to show my gratitude about your educational content? So if you really want to support, like do something that actually gives me money, not just get an access to the Discord server, right, but actually give me money, you can check out the donate command, right? So there is a link which explains how to give me money. Right. So, but the problem with that option is that it's very inconvenient option. And if it's not suitable for you, don't feel obligated to use it. Just enjoy the content, okay? Never feel obligated to give me anything. Right, so if you want to actually support me, not just get the access to Discord server, but actually support me, consider this. It is not convenient. Don't worry about it. Just enjoy the content. That's it. So, anyways, depending on how situation in the world evolves, we may have more different convenient options for donated in the future. It depends. We'll see. It depends. It depends. We need to push a bunch of registers, right? So the point of coroutine yield, I suppose, capture the current environment and pass it to the switch context. Right? That's what it's going to be. Just capture the environment, pass it to the switch context. So I really like this kind of approach. So let me take a look. So set jump s, right? So we need to save all of that scheiße. So this is this kind of thing. Emacs. Depending on the current indentation mode, it starts to freak out about tabs and spaces and stuff like that. This is actually kind of funny. Look at that. So it doesn't freak out about tabs in here, but it does freak out about tabs in here. And this is because these two different files are in two different indentation modes. Right, so this one is in a space indentation mode, and this one is in a tab indentation mode. Right, and if you use tabs in a space indentation mode, it freaks out and it's just like, bro, you have tabs! Ew, disgusting! So let's quickly replace tabs with spaces. There we go. So that's much better. So let's maybe say something like a stolen from Musil. Honestly, it's actually kind of surprising how much code I've stolen from Musil. I really like looking into Musil because it's just like it's a simple C library, right? Every time I want to know like what C library is doing in this situation, I just look up Musil, right? So It's just like way convenient, way more convenient than trying to understand glibc. Missile is really good. It's insanely good, right? So this is just like an implementation of set jump, and yeah, it's pretty straightforward. It just saves the registers to the buffer. Nothing particularly special. Okay, so this one is pretty straightforward. So it just sequentially, you know, saves these registers, right? Then it saves the RSP without current return address. I don't think we need that, honestly. I don't think we need that. So it also saves RDX, right? So it also saves RDX. So because the arguments go from left to right, so you save left argument to the right one, right? So it goes that way. It's AT&T. Then it saves RDX, and then it saves the return address, and then it saves RDX again for whatever freaking reason. Oh, it's just, yeah, I see. So these two are saving this kind of stuff. Oh, and even RDX is just like this thing. Right, so essentially, let me try to do the following thing. What I'm gonna do, push. Maybe I can even grab all of that shit. Like literally copy pasting code from USL. Like literally just copy pasted code from USL. That's kind of funny. But what's funny is that we don't need to save it into the buffer. What we can do, we can just push all of these registers. Right, so we're pushing them. So, and they're going to be on the top of the stack. So then later, when we kind of like restoring the context, right? Let's imagine that we have another function here, coroutine restore context, right? So restore context. I guess what we're going to be doing, we're going to be like literally doing the same, but in reverse, right? So let's imagine that restore context accepts the RSP in first argument. So that means we'll have to do RDI RSP, and then just do this thing, but in reverse, right? Just do this thing in reverse, right? Reverse, can I reverse lines? Reverse region. Damn, can your Vim do that? It probably can, but I don't really know how to do that. So we just push them in particular order. Oh, look at that, even the move is kind of inversed. Right, well, I mean, you have to do something like that. Damn, it's just like, it's literally like an inverse of that. So, and essentially what's going on, when you call yield, what you have on a stack is a return address. Then you push a bunch of registers in here, right? Stack grows from right to left, just a reminder, right? So in x86 and also ARM, the stack grows from right to left, so the top of the stack is actually here, right? It's very important to remember, and it's very important to develop your mental model of a computer so the stack grows from right to left. And it makes a lot of sense when you get used to that. So essentially, when you call yield, we have a return address, then we push a bunch of register, then we take that RSP and we pass in it to switch context. And switch context will probably just save the current RSP. So then when we're restoring the context, we get the stack as this, right? So we get the stack as this, basically switching to that stack, then popping all of these things, so which means that RSP is going to go here. And now we have to jump to the return address. Well, I mean, to jump to the return address on the stack, you just return again. That's kind of the point of the return. Return is basically jump, except it takes its address from the stack instead of the operand. Wait, I never thought about it this way. It's literally the same instruction. Yeah, it's the same instruction. That's kind of funny. Why do you need, like, I wonder if you, well, I mean, okay, a return also pops it. You can try to do something like a jump RSP, but that will jump, but it will not remove the return address. So return also like pops that that address from you. You can always do that yourself, right? Pop RDX and jump, but I mean, there is an instruction to just do that. So, damn. So, and effectively, it returns from the yield call. Huh. Damn. That is so cool. But anyways, so, and what's funny is that now, within the switch context, what we have to do, we just have to call coroutine restore, right, coroutine restore context, but on a different routine. Huh. But now we need to have some sort of an array of contexts in here, right? So this is going to be contexts, and maybe we can have a capacity. Well, okay, so we want to have a dynamic array, right? So we don't want to be hard coding the size of the context, right? So we want it to grow automatically, right? So let's actually introduce the dynamic array, the usual dynamic array. So contexts, something like this. There we go. So in here we're going to have context, which is items. This is a classical dynamic array that I use all the time. You know, the one for which the clip on Twitter been reposted and went viral multiple of times, right? So I'm pretty sure everyone at this point is familiar with DA append macro, right? So everyone knows DA append macro in here, right? So everyone saw it on Twitter, so we're on the same page. Okay, cool. So this is the dynamic arrays we're going to be using in here. DI append, да append, блядь. Да append. Да. I'm sorry. Capacity. DA stands for dynamic array, okay? So that's what it stands for. I can steal it from Nob, I think. I don't have Twitter. Good. This is a good decision. This is a good decision. So, where is my Nob? Ah, where is my Nob? Ooh, somebody stole my Nob. DA append. So here it is. I'm gonna just like literally steal it. From here. I lost my keyboard. There we go. So DI append, and honestly, like I don't want to have a nob prefix in here, so I'm gonna quickly remove that nob prefix. So fuck that. Fuck nob. Fuck that nob. So, and let's just create like a contexts, right? So initially it's going to be 0 and stuff like that. And we also need to keep track of like the current, you know, the current context, So the cool thing about this approach to dynamic arrays, right? People quite often tell me, like, why don't you define a macro that, you know, generates this kind of structure definitions? First of all, when you define macro that defines functions, you greatly reduce grabability of your source code. Looking at you, Lagrange. So if you don't know what the fuck am I talking about, I really recommend you to watch the video Lagrange UXN. Right. Watch. This is 5-hour session. After watching all of the 5 hours, you will understand why it is 5 hours, and you will also understand why I don't like macros that define functions. It is all in that specific video. Right. So, second of all, it allows me to actually add additional fields that have nothing to do with the dynamic array. I can always add another field, current. Right. And by just adding that field, I didn't break this macro. Macro will still work with this structure because the only thing it cares about is the presence of 3 fields, capacity, count, and items. If you have more fields than that, it doesn't give a shit, right? You can just use them. So you can have more fields in here than the macro actually needs, right? So which is kind of difficult to achieve when you standardize the way of defining dynamic arrays. Stop standardizing things, honestly, like just be creative. Right, you have a macro that treats any structure with these 3 fields as a dynamic array. Use that to your advantage. Use that to your advantage. So you can add more fields. The macro doesn't give a shit. So it can be more flexible than that. And also, it gives you an opportunity to give creative names to these kind of things. It's just like it's overall better, in my opinion. Boeing is being very creative with doors. Anyway. Buy more RAM. Well, I mean, the only reason why malloc will return null is that because you ran out of memory. And if you ran out of memory, that means you're poor. Just stop being poor and buy more RAM. Obviously, it's just like it's that simple. There's no even need to properly check for this kind of error. The only thing you have to do in here is assert. So anyways, but no, for real. So I think malloc will even return you something if you try to allocate more memory than you have. Because on a modern 64-bit operating system, we have a virtual memory, right? So just because you allocated a lot of memory, it doesn't mean that it's going to commit all of that memory until you try to use all of that memory, right? So it usually will return null when you literally physically ran out of memory and ran out of swap and ran out of everything. But at that point, your operating system is basically cooked anyway, so you might as well die. So that's what I'm saying. It's not like we're developing something like embedded where you really have a hard limit on memory and you need to handle the situations when you ran out of memory and stuff like that. No, this is just a user operating system, and when malloc return null, your operating system is basically cooked and there is nothing you can do about that, just fucking die anyway. So yeah, it's kind of a solved problem. You don't have to think about it too much. So yeah. So you don't need to check for null because you have bigger problems than segfault. Exactly. When malloc returns null, you've got bigger problems. Much bigger problems. Or maybe no problems at all, because there's nothing you can do. Just relax. Enjoy the process. Windows? Who uses Windows? Anyway. So current. So we have current, and this is where we're going to be storing the current thing. Okay. So we also need to have something like a coroutine init. Coroutine init, but let's not think about it too much. So essentially, what we can do, contexts current, and we want to do actually context items. So this is the current context. So in a current context, we want to save that RSP that we captured from the yield, right? So yield captures the environments and returns the RSP, and we just say, okay, so this is the current RSP of the context. So next thing we need to do, we need to switch to the next thing, right? So we have to do something like +1, and then we have to mod this entire thing with count, and we have to reassign the whole thing like that. I always wondered, I mean, the easiest thing to do here would be to do something like that. It would be kind of cool if there was a language where you can do plus equals, but also by mod. You know what I'm talking about? So it's just like plus equals, but also by, but maybe it's not that big of a deal. All right, whatever. So, and yeah, so after that, we can just take this RSP of the next one, and I guess just restore its context, right? Right, we just restore its context, and then with the restore context, right? So if we switch into this one, we know for sure that this thing already contains saved context. It already contains the register and return address because it was yielded from at some point. Right, so it was yielded from at some point, so we just pass it in here, and the restore context is going to actually restore and just okay, so that's about it actually. I think that's about it. So the only time you're not going to have the context, oh yeah, something like that. I guess holy shit, I didn't look at the chat after asking. Okay, you guys are too creative. Can we actually do something like, just a second. So we're gonna do +1, but can I then do mod like this? Do we even have a mod equals operator? Looks like we have, right? So I forgot to define these things. So this is going to be coroutine restore context. So RSP. Okay, so undefined reference restore context. So in ASM, because we never actually exported this thing. Okay, so extern, it actually has to be public. All right, and it's segfaulted. But I mean, it's not supposed to work yet anyway, right? So, but it's supposed to compile, right? So, is that better? It's like +1 instead of like assembly style. Nah, I think it's too much. I think it's too much. Let's listen to that. Anyways, I don't think ++x is left-hand side expression or L value. I don't think it's an L value. So it's pretty much R value. Yeah, I don't think it's gonna work. I think this is fine. I think this is fine. Anyway, so the only time we're not going to have this kind of situation and when we do init. When we do init. Or do we? Right, so we need to introduce coroutine init. Right, and init is going to be kind of similar, right? So it will take right, the current RSP. I see what we need to do in here, chat. I actually see what we need to do in here. So I think it's literally just like yield, init, right? It basically pushes the current state, so init is supposed to create the coroutine, the context for the current process, right? The context for the current process. So I don't know how to call this function. Maybe like init first, right? Init current, right? Init current. So you're supposed to call it once before using any coroutines or anything like that, right? So init current is going to be an external function, right? So it's going to be an external function, right? And then you just do something like that. And obviously it will accept void RSP, right? And it should basically append the first context in here. So it's going to be di append. All right, so this is going to be contexts, and this is context RSP, right? So, and maybe we can even reserve the index 0 as the index of the coroutine that is the main coroutine, coroutine start. Maybe we could call it coroutine start, right? So sort of like a start. Right, so you basically, yeah, we can do something like that, coroutine start. Yeah, let's call start. So we do init, and it does its thing. So this is the first ever coroutine. And funnily enough, after doing a single yield, it should not segfold anymore, right? So because you already have something, so you save it and you restore it. So if I try to now build the whole thing, well, there's no di append because I didn't fully remove knob in here. How that happened? I can't believe that. I can't believe you've done this. So what do we have in here? Oh, there's no real lock. Okay, so also there's no assert. So real lock, do you want something like stdlib? And it probably, yeah, it also probably wants to have something like assert. Are you happy now? Coroutine init. Okay, so it's not available. Let's make it available. So it is now available. Yeah, so, and if we try to run this entire thing, it still segfolds, even though it's not supposed to segfold, in my opinion. I'm just saying. So let's just try to initialize the whole thing. Still segfolds. Look at that. Fascinating. What if I don't try to call this thing? Now it doesn't segfold. Okay, so that's very interesting. So something happening in init. You know what? We can actually debug that. Who said we can't fucking debug that, mate? Who said we can't fucking do that? Fuck you, we can do that. Okay, so maybe I can do W extra, just, you know, so we don't miss all those juicy semicolons. And let's enable the GDP, right? So I'm gonna just do that. And let's just open that in a debugger wagga. Yeah, something got fucked up big time. So I wonder what exactly. So we can try to do break main. All right, and just run this entire thing. Okay. So let's enable the assembly, right? So it just calls into coroutine init and its assembly part, right? So let's just jump into that. And this is exactly what we see in here, right? Nothing particularly special, right? So I just go through all of the instructions, right? As you can see, we pushed all of that in the stack. Then we save the stack into RDI. Then we're jumping into coroutine start. Okay. So looks like we jumped there successfully. Now what we're doing, we just like di append into the context, right? So I can just do that. And you telling me that appending this thing is going to segfold. Okay, it didn't. Ah, I know why it's segfolded. Because we don't have a proper return address after that. Yeah, we don't have a proper return address after that, so... But wait a second. Are we ever going to return into init? Wait a second. So what if we just like... okay, so what if we forget everything? Init void, right? And it's a C function. Fuck all of that. Right, we do init and we just like put like an empty thing in here. We're never gonna return into this point anyway, because the next time what we're gonna do yield, and yield will save the current context at this point, overwriting whatever we had in here anyway. There's no point to capture the environment in init. It's pointless. It's gonna be overwritten by the next yield anyway. What the fuck? Like, why do I even knew all that shit? Wait a second. So fuck all of that. So yeah, so just like, yeah, just put something, just reserve the cell for the zeros coroutine and just like continue. Yield is going to capture the state anyway at needed point. So yeah, so that means here I can just do that, and it doesn't segfold. Look at that. It doesn't segfold. So basically after the yield, it saved its own environment, then switched the coroutine. Since it was a single coroutine, it switched to itself and then restored its own environment and continue executing. We can even try to see that. I'm actually really curious. Really like that. Just a second. This is kind of funny. Right. We already have GF. Right, so break main. Right, so we're gonna do run. So I step into the init. Right, so we can even take a look at the current conc texts. So context, right, context, there we go. So as you can see, the count is a 0, right? So then we do n, and now we have the first one, and RSP is 0, which is understandable. Okay, so now let's take a look. We're about to call coroutine yield. So we step into that, and as you can see, we're pushing everything under the stack. We save in the stack, then we going into the coroutine switch context. Right, so let's go back in here. So we are, you know, saving the RSP, right? So here is the saved RSP. Then we are switching the current, since we only have one current state the same. And now we are about to jump into the coroutine restore, right? Coroutine restore. And here what we're doing, we're restoring the same state that we just saved, right? And now we're returning back, and we return back in here. Right, and then we exit out of the program. What a useful program we just wrote. Isn't it cool? It's actually kind of funny, I like that. Yeah, anyway. So we need to implement something that will create more new, different kinds of coroutines. Right. So we need to do, like, okay, so let's actually do coroutine, like counter. Maybe I can steal the counter from here, right? So that's what we need in here. So like counter, right? And I want to do coroutine go. So let's take a pointer and let's pass it in here. So what's funny is that, do we need to capture any of the environment when you do go, right? So my idea is going to be that when you do go, you just register the counter in the context array and then just continue executing. So you're only going to switch to counter after the next yield. So it doesn't start executing right away. Right. So it doesn't start executing right away. It only starts executing on the next yield. So I guess that makes sense. So that means for the go, at least we don't have to wrap it into assembly. Maybe we'll need to have a little bit of assembly on a low level. We'll see how it goes. Could be, yeah, it could be also kind of interesting to pass some arguments. I agree with that. So basically accept void arg here and just maybe accept like for how long you want to count, right? So just you can do it like this, and then here we're gonna, I don't know, like cast this entire thing to int, right? So to int and just do something like that. Yeah, don't even have to do anything in here, right? So, and we pass it as a void star because you can either pass a pointer to a structure or you can pass, you know, a primitive value, just store it in there, right? So basically how I think pthread create works, right? So it has a start routine in pthread and it accepts void star, which means that you can use this void star to store a pointer to a structure, or you can use the pointer itself to pass some sort of a number, right? To pass some sort of a number. But I don't know, I don't want to go into that yet. It's kind of difficult. Actually, it is not. Actually, it is not. Since the argument, you pass argument through RDI, you can make RDI part of the context that you save on a stack. So essentially, when you register a new coroutine, you need to prepare this sort of stack in here, and you need to prepare the value for RDI. Yeah, you need to prepare the value for RDI. And then when you first enter the coroutine, it will appear like you passed an argument there. So yeah, that's kind of interesting. So, but I don't know. Let's keep it simple. Let's keep it simple. So here is the coroutine go. We're already streaming for 1 hour, right? We're already streaming for 1 hour. Let's actually make a small break. Let's make a small break. I'm gonna make a cup of tea, and after I make a cup of tea, we're gonna implement coroutine go. Sounds good? Sounds good? Tamagotchi? Let's go. All right, we're back. So what we need to implement? We need to implement coroutine go. So let's go. So void coroutine go, and we accept the function, right? So which doesn't accept anything, something like that. All right, so we need to prepare the stack, right? So, and since we're programming in C, we actually have a luxury of just doing a more complex memory allocation, right? So we can just literally malloc a buffer. I don't fucking know, right? So maybe we can have something like a stack capacity. So how big of a stack do we want? Do we want like a 1 kilobyte of stack? What's the size of the stack in Go? Right, so I think it was like 8 kilobytes or something. Right, so I don't remember. Malloc these nuts. Yeah, thank you so much. Really cool. So this is a stack capacity, right? So we can just do something like this. And then, so 4 kilobytes on Go routine by default. Okay, so we're gonna do 4 kilobytes then. So there we go. 4 kilobytes. And then we can just do di append to the contexts, and we can just do context RSP. Right, and that's basically how we register coroutine, unless it's not actually. This is not how we do that, because the stack grows from right to left, right? So we allocated the buffer for the stack, and since we just returned malloc, this is where it points to. So when the program will try to push something on the stack, it's going to be pushing it to the left in here, so it's going to underflow. So what we have to actually do, we have to set RSP to somewhere here. So that means what we have to do, we have to actually add stack capacity in here. And we're kind of losing the pointer to the stack at this point, which means that we're going to leak it at some point. Maybe we need to save like a base pointer to the stack somewhere, right? So then we can actually easily to deallocate it. Right, so maybe we can store that in the context, right? So stack base or something, right? So this is a stack base, and in here we're allocating stack base, right? So this is a stack base, and then RSP is going to basically stack base plus the stack capacity, right? Something like that. So, and in here we can say, okay, this is RSP equal RSP, and this is a stack base. Right, so we're just like saving this stack base, so later when the time comes, we can deallocate it. Right. Also, I think this kind of thing is kind of dangerous, right? Because the arithmetic operations, pointer operations are not defined on void star, right? Even though I think it will not complain too much. God freaking damn it. You have to add extra parentheses in here. Yeah, you had to. because no, what just happened? Because I hate C. I hate C. So essentially, since di append is a macro, its arguments, it views its arguments as stream of tokens. So this stream of tokens is first argument. Then it looks at the stream of tokens until the next comma. So for it, this is the second argument, right? Because this is the tokens until the next comma, right? And then this is the third argument until the next comma, and this is the fourth argument. So this is actually not 2 arguments, this is 4 arguments. Collateral moment, yeah, it's collateral moment. So to sort of tell it that this is not actually separate arguments, you just wrap it in parentheses like that. Thank you, C, very cool, exactly. This kind of shit is a bane of my existence, like I swear to God. So yeah, anyway, so this is what we had to do. So it doesn't want to do some of this stuff. Unused argument F. And this is where it gets very interesting. So we actually need to massage the stack a little bit, right? So just allocating the stack and like handing it to the to the context is not enough. The top of the stack should look like after yield, right? And this is very important. So after yield, you have a return address at the top of the stack, right? Plus a bunch of registers. Like this. So we need to prepare a stack so it looks like this. So we need to append the return address and a bunch of registers. So we can assume that all of the registers there are going to be basically 0, right? So let's just initialize them with 0. And as a return address, we can use basically F, right? So we can use basically F. By the way, so I was talking that the pointer arithmetic for void is not defined. I need to actually cast it to char, right? So it is not defined. So when I cast it to char, it is going to increment them by 1 byte, right? So, and this is exactly what I expect in here, right? So maybe after that I need to cast it. I don't have to cast it back. So you can, if it's char star, you can assign it back to void star. All right. So all of these things, the return address itself and the values of the registers are 64-bit integers. So what we can do, actually, we can view pointer to RSP as a pointer to array of uint64t or something. That's what we can do. Right. So let me do something like this. So this is going to be int. So after that, what I can do, I can decrement RSP by 1, right? So imagine that we're pointing at here. By decrementing RSP by 1, I'm pointing at here, which means I can do RSP, I can dereference it, and I can now save a pointer to a function like this. So, and that becomes kind of a return address. So essentially, I can do something like this. I can do something like that. Right, so that will, if I understand correctly, that will return the already decremented value, which I can dereference and put f in here. So this is an equivalent of pushing onto the stack, but in C. So unnecessary increment by stack capacity. Yeah, this is true. This is true. Thank you so much. Right. So this is basically like pushing on the stack. This is pushing on the stack, which is rather convenient, honestly. Right. So, and the next things, if I take a look at the new ASM, here is the stuff we have to push in here. So we can just like push zeros in here. Right. So maybe I can do something like that. Right. RSP equals 0, and this is the, yeah, something like this. Yep. So this is going to be RSP, and after pushing all that stuff, we're going to be pointing at here. So now it should look like, you know, like the state of the coroutine after the yield, but we kind of fabricated it. Right, we kind of fabricated it. Hopefully that will work. But furthermore, when the coroutine returns, right, so when the coroutine finish executing, it needs an additional return address into finish coroutine function, right, into finish coroutine function. So which we'll have to put somewhere here, right? So this is going to be coroutine finish. So then the current coroutine can be basically removed from the context. So let's actually put this stuff in here. And in here, I suppose we can just do, I don't know, assert 0 to do coroutine finish, something like that, something like that. Okay, so I guess that may work. That may work. Do we need anything else? Actually, I don't think so. So we're gonna be in the finish. We're gonna be deallocating this stack base, right? So that's what we're gonna be doing. We're gonna be deallocating the stack base. All right. So let's try to run this entire thing. So char star incompatible. Oh yeah. So that means it's not a void star anymore. So that means I have to do something like 64T. So what else do we have in here? Coroutine. 64. So yeah, I need to now cast the pointer 64T. Can I do something like that? I guess I could. You know, can I just do some stupid shit like so? because it's kind of pointer, right? So all of these things are kind of pointers. Can I just do something like that? All right. So will it work? Yeah. And by the way, so let's get rid of these things. So this was basically hypothesis. Okay. Wait. It just yielded 0. Okay, it works. Look at that. Yeah. Let's create 2 coroutines, and yeah, it works. So in terms of assembly, that's the only assembly we need in here. Which raises the question, maybe we can still implement that in C, but with naked and inline assembly. Because it's not that much, right? Do we need anything more? So we only haven't implemented finish, right? So we only haven't implemented finish. Do we need assembly for finish? I don't think so. I don't think we need assembly for finish. I don't know. Anyways, so let's try to invoke finish, right? So I'm gonna indefinitely yield, and let's see how it's gonna go, right? So it isn't like true, whatever. So this is boolean. Segfaulted, though. Segfaulted. Sus. I didn't expect it to segfault. Didn't expect it to segfault. All right, so that's interesting. So it went fine, then it reached the coroutine finish situation, and it couldn't handle it. All right, coroutine finish returned to garbage. Yeah, so it kind of returned to garbage. So, oh, well, I mean, assert is supposed to kill the whole thing. Right, so coroutine doesn't know where to return, but like I would expect that it's going to kill it. All right, so let's actually try to debug this entire thing. Yeah, so break coroutine finish. Let's just try. Okay, we reached it, and as you can see on the stack we do have garbage, so it has nowhere to return. Right, so then we do next, and it's just like, ooh, coroutine. It crashed within assert. Wait, was it trying to allocate something on the buffer? The stack is garbled, I guess, yeah. Okay, can I just abort or something? Okay, so it aborted. What if I print something in here? So to do coroutine. Okay, so something with assert. Wait, wasn't recently CVE found for assert or something? Like, apparently assert is a rather complicated function, isn't it? It's not it. Oh, okay. But my point is not that this is a CVE. My point is that if there is a CVE, the code is probably complex, right? So, and since the code is complex and you are literally at the bottom of the stack, maybe something weird happened in there. GC expects the stack to be aligned to 16 bytes. Maybe that's a good point. That's a good point. So we probably have to align it. So to do align this stack to 16 bytes or whatever, right? So that's a good point. We'll have to do that at some point. I needed more than 4 kilobytes, so we can allocate more. But I mean, a board just works. A board just works. If I had to get the assert tries to unwind and your stack is weird. Oh, that explains it. Okay. Huh, I guess I learned something. So yeah, this is the reason why it's worth doing weird random shit like this, because you learn things, right? How else you expect to even learn any of these things? Read a book in 2025? Serious? Right. So when the assertion function in GNU library versions fails, it does not allocate enough space for the assertion fail a message string size information, which may lead to a buffer overflow if the message string size aligns to page size. Ha. Yeah. So let me click. Okay, that's very interesting. Cool. I'm gonna add that to the description for anyone who's interested. So what we need to do in here, chat, we need to delete that bir. We need to delete that bir completely. How are we gonna be doing? So we can move the array around, can't we? We can try. One important way in which a stack is weird, RBP points to the start of the stack and it's immediately pushed after RT. RBP points to the start of the stack and immediately pushed after RT. That's a common convention. That's what you mean. Maybe. But I mean, I was just following set jump in here. I mean, I can basically change the order in here like this. And will that help? I don't think so, right? It doesn't really matter in which order we just put these things. So, but we can try. I don't think it's going to change anything. Okay, so let's actually focus on finishing the whole thing. So, just I'm going to check. Nah, it's still false. But if I try to do something like this, it doesn't false. Anyways, so it's just a weird stack, so it doesn't like the weird stack. So contexts, items. We want to do something like a mem move. Right. So this is the destination. So let's think. We have a bunch of contexts. Something like this. And they usually have some sort of like indices, right? So this is 0, 1, 2, 3. And let's imagine that I want to delete this one, right? It points at 1. So that means I want to, the destination is the current pointer. So I want to move this chunk of bytes to here, right? So that means I'm going to do contexts, items, contexts current. And this is kind of my destination where I'm moving those elements. From where I'm moving them, I'm moving them from the next one. Right, I'm moving it from the next one. And the question is, how many bytes, and this is very important, how many bytes I want to move in there? Memmove is always a pain, I agree with that, but I mean, we have to do something here. So we have to move 2 elements, right? So we have 4 elements in the entirety of the array. It's definitely something to do with the amount of elements minus the current element that we're trying to remove. But that results in 3. But we need to move 2, so that means we need to do extra minus 1, I suppose. Is it consistent? So if this thing was 2, yeah, so that means we'll have to move like 1 element. So it's a count minus current minus 1. But this is the amount of elements, that's the problem. We need to multiply that by the amount, by the size of the element, like this. I hope I didn't miss anything. So after doing this kind of stuff, we have to decrement the count. Just swap the last element with the current one and reduce the size by 1. We could try to do that. Free the stack. We also have to free. This one is actually weird. Guys, freeing the stack is, you have to be careful. We're currently on this stack. So, just saying. So I don't think doing something like free stack base is a good idea in here. So, oh shit. How the fuck do I free the stack then? Live lobotomy. So self lobotomy. Yeah, so how I'm currently on the stack. How do we don't release the stack. Just let the process, I guess. Let the main routine do that. Yeah, so I think it has to be done in a different routine, in the main routine or something. So yep. Return oriented programming. So let's not think about it. Let's just let it leak. We have enough RAM. How much RAM do I even have? I have, where is the RAM? 2 gigabytes, 3, 14 gigabytes. I have 14 gigabytes of RAM. I think I can afford that. Just let it leak. Let it leak, oh let it leak. Memory costs nothing. Let it leak. Let it leak. Let it leak. Let it leak. Oh, let it leak. So I'm going to be swapping this entire shit. Like, and you see, we don't really have stuff for swapping. Right. So let's have something like context. Right. So this is going to be T. And I don't like these huge ass things, right? Know what I'm talking about? So this is gonna be count -1, maybe even current. So the thing is, okay, so we saved current into the variable. That means it is safe to override the count with count -1. Right. So then we just do something like this. There we go. I swapped it. I literally just swapped it, and then I can do context count -1. Yeah, that's a good idea, honestly. That's actually a good idea. So yeah. So that also means current. What if the current is already equal to the last one? That means, well, it's going to be swapped with itself. That's understandable. But also it's going to overflow, which means that we want to, just in case, maybe kind of clamp it to the count. You know what I'm saying? You know what I'm saying? Just like clamp it to the count. After that, I think what we have to do, we have to just switch the context, right? So yeah, so we have nowhere to return in here, chat. We literally have nowhere to return. So the only thing it makes for us to do is to switch the context. So new asm, restore the context, right? Restore the context. Yeah, it will restore the context of other routine, and that routine is basically done. Right, so yeah, it's basically cooked. Restore the context. Restore the context. Let's go. Let's fucking go. Let's fucking go. Let's fucking go. Let's fucking go. Right. So let me see. I think that worked, chat. Because the mother flipping this thing keeps yielding to itself and never finish. Brovskis. You know what we can do? We can do contexts count greater than 1. I'm sorry if it was too loud. Oh, okay, so that makes a lot of sense, right? So it's actually super convenient. So while you have more than one context, which means that you have like non-main contexts, you just keep yielding them until they all die, and it just exits fine without any segfaults or anything like that, and it's implemented in C, and you are not even limited to freaking 10 coroutines. Holy shit! Yo. Bro, and the fact that the assembly part is so small is actually kind of... This is the entirety of assembly part. This is the entirety of assembly part. This is nothing. We should re-implement it in like GNU assembly, I think. Right, I didn't want to do GNU assembly because I thought it's going to be super complicated, right? So I didn't want to write anything complicated, but we can actually port that to GNU assembly, I think. Right, we should do that. We should freaking do that. Okay, so I want to actually try some other things. So right now, coroutines are kind of like, they're the same size. I want to have one of them be shorter than another one. So you can probably achieve that by passing parameters, but do I want to do parameters? Let's fucking do parameters, why not? Right, so we do RBP. One of the things we probably have to do, we have to also do push RDI for whatever reason, right? So, yeah, I don't know, is it going to be too much to do RDI? Because pushing RDI will enable us to do a very cool thing, right? It will enable us to do a very cool thing. So as we recover and stuff, now this thing is supposed to accept the argument, and when you do coroutine go, this thing is supposed to accept the argument, right? So this is RDI. Now we have to do void arg, and here we just do push RDI, and we just do that arg. So then after restoring from that new thing, it will feel like it has an argument, right? So because it's in RDI, it will restore the RDI register as well, right? And it will appear like it was called with an argument using Linux x86-64 convention. So that way we can even pass parameters into the coroutines. Yeah, that's actually kind of cool. So let me see. So that means here we can say, okay, this one has to go up until 5, right? So this is going to be something like this. And this one is going to be up until 10. Yeah. So one of them is going to be shorter than another one. So I just want to see how they survive when one dies before another. Well, technically, one still dies before another. Right, but I just want to see that. I just want to see that. Chat! These mother flipping coroutines still have an access to the context. You know what that means? That means we can actually print the number of the current coroutine that is executing. Holy shit. Well, this is so convenient, right? Implementing coroutines in a high-level language actually gives you more opportunities, right? So this kind of stuff in assembly would have been actually kind of difficult. So we can do current. So we can actually inspect our own context and just tell, okay, so I'm the coroutine 1, coroutine 2, and coroutine 3. We can actually see that. So... All right. So that's super cool. So, and in here, we'll probably have to do something like, int arg, and we're going to put n in here. So is it going to actually, holy shit, fuck you, it works. Yeah. And in one of them was shorter than another one, it was... Damn, bro, I have actual coroutines and I have full control over them. And they're not even magic free. I love when there's no magic and I fully understand how this supposedly magical thing works. Like I really enjoy the fact that I have a full mental model of what the fuck is going on in here. This is so fucking cool. Okay. I think, yeah, I can now pass parameters and it's like, damn, bro. We need to re-implement it fully in GCC, right? So I think it's worth it. Like I thought it's not gonna worth it, but I think it's worth it now. No magic program is the best program. Yeah. It's so cool. It's really fucking cool. All right. So how could I implement the yield? Let me see. I'm going to comment out yield. Right, so if I try to build without yield, it will not link, which is understandable. Right, let me copy paste it in here somewhere. So this is how it's supposed to look. So now I can say yield. We need to make the function naked, so it doesn't do prelude and epilogue or whatever. Prologue and epilogue, yeah. So GCC naked function. Just in case, I'm gonna Google that up off screen. You never know. You never know. The word naked is kind of a dangerous word. Like you never know the Twitch to as and stuff like that. All right. So using the naked attribute for functions in GCC. So you can simply call from naked function provided that the called function. So attribute arm ports to indicate that specified function does not need prologue, epilogue sequences generated by the compiler. Okay, but I want to see an example. Where do you slap the attribute? Where exactly do you slap the attribute? So arm developers function attributes, right? As GCC ASM is AT&T syntax. Yeah, it is AT&T syntax. But I think it's fine because we don't really have a very complicated code. So I suppose it goes after the function declaration like this. All right, so I'm gonna put it in here and it has to be naked. Okay. So now if I just don't do anything in here, I expect this thing to segfault. before return type. Okay, so I don't know, like this is what documentation says. Anyways, so if I try to do that, coroutine attribute should be specified before the declaration in the function definition. Before the declaration in a function definition. Is that what you want? Okay. It was a legal instruction. Okay. This is bizarre. Like I'm really annoyed by GCC attributes because I never fucking know where to put them. They made it so convoluted and it's just like, bro, what the fuck? Why do you do it like that? It's just like, why it's unclear. So attribute syntax. Okay, so C attribute syntax describes the syntax with, like, really, you look at that code. Like, this is why I'm annoyed at their attributes. Look how much fucking text do you need to explain the syntax of the attributes. GCC developers, are you okay? Like, seriously, it's a fucking attribute. It's an attribute, a thing that other languages had for many, many decades. It's not a computer science, a rocket science, that's what I want to say. It is a computer science, actually. What the fuck am I even saying? So, okay, so can I just, so it's after the return type, right? So, oh, okay, so that's cool. But if I remove that one, it's, okay, there is fundamental difference with and without the naked attribute. With the naked attribute, it crashes with the legal instruction. Without it, it actually hangs, which is kind of expected because it probably hits this infinite loop, which actually aligns with my hypothesis about how all of that stuff works. It confirms my hypothesis. Okay, so we mark it as naked, and now that means we can put inline assembly in here. So I don't really know how to use inline assembly. I suppose, okay, so let me see, just to see. Honestly, I can, yeah. Just to see inline assembly. Let's find out. More GCC documentation, GCC inline assembly Wikipedia. Okay, so you literally have to do the strings. Why is it in Russian, by the way? I guess that's how we do that, right? So, okay. So we have to maybe copy paste all of that stuff in here. Let's put it like this. I can probably take the entirety of this thing. Right. And if I understand correctly, so instead of using push, in AT&T you have to do push Q. Right. Furthermore, what you have to do, you have to prefix the registers with $. Move, it also has to be move Q. So what I remember about AT&T, I don't like AT&T, but I do remember a few things about it, is that the instructions have to have an explicit prefix about the size of the operands, right? So hence the Q, right? So it's a quad 64 bits. We are operating on 64 bits. So another thing is that source and destination are swapped, right? And also prefixed with dollars like this. So as you can see, it's by definition more noisy. Dollars, I mean percents, I'm sorry, like I confused them. It's just like, so it's by definition more noisy because we had to add more characters in here. And that's one of the reasons why I don't like AT&T. It's just like, it adds noise without any reasons. Right, and I'm not sure about GMP. Maybe I'm gonna leave the GMP as it is. And I don't even know if, you know, I can just refer to the name of the functions like that. I don't know. Suffixes are kind of optional nowadays when both operands are registers, but I might be hallucinating. We'll find out. So I suppose now what we have to do is to turn all of that into strings. Right, so... So, and I also have to specify new lines in here. So because it literally dumps that stuff into assembly as text. Right. So I wonder if this is going to be enough. I'm really curious if this is going to be enough. All right. So let's give it a try. Motherfucker just worked. The fuck? Okay. Let's fucking go! Let's fucking go! Who needs FASM? Who fucking needs that stinky FASM if you have built-in GNU assembly? Anyway. So this is actually kind of cool. So we can actually keep it self-contained and reduce the amount of moving parts in some sense, even though I don't like GNU assembly, right? So yeah, I mean, okay. So what about restore context? I suppose this is basically the same. All right, so restore context. Okay, so we're gonna make it a naked. I'm resisting the urge to make your mom joke, but I mean, that's fine. So this one is going to be something like that. This is the new line. Okay, so this is Q. Then this is Q. This is a very special weird dollar. Then we swap the source and destination. And that should be it. Let's also indent this stuff a little bit. So this is awesome. It's kind of a weird indentation in here, but I mean, it's probably fine. Okay. So now another interesting question. Can I now just get rid of this entire stuff? Right. Can I just get rid of this entire stuff? Like this. Coroutine is fully implemented in WASM. Wait a freaking second. It worked completely accidentally. Fuck. This is funny. This is funny because we... I never referred to this argument. But it still worked because I'm directly doing that. I remember there was a way to kind of like... Man, I don't even know. What do I do with that? So can I just say that I don't care about RSP, but I still do care about RSP? I think I can. Yeah. So I can do something like uint long int long. Yeah. That's really cool. So now I can actually get rid of the coroutine UO completely. It doesn't exist anymore, and I can get, yeah, so it doesn't exist. So it's a single C file. It is literally a single C file. How fucking cool is that? Long int is still 32 bits. GCC doesn't complain. I don't think so. I think long depends on the architecture. Int is 32 bits, but I think long depends on the architecture. Long is 64. On 32-bit platform, it would be 4. So yeah. Only on Windows 64. Okay. So that's pretty cool. Can I use the shed in C3? That's a good question, actually. Can I use this shit in C3? I need to factor this out to a separate library of some sort that I can reuse in C3 or something like that. Long int. Okay. So I suppose we don't really need this coroutine experiment scheisse, so I can safely remove that. So I'm safely removing that, so we don't need any of that stuff. Honestly, yeah, so let's just remove all this stuff. So I can only do main, and this is the new main. Okay, that makes sense. Let's create coroutine, C. And let's move everything related to coroutines there. So here is the DI append, append. Here is the context and the context stuff and so on and so forth. That's understandable. Coroutine init and some other things. Finish. So we're only not going to move counter, right? So the only thing we're going to have in here is the custom coroutine and the code that sort of facilitates coroutine-ness. Okay, so and in here we can probably do some sort of a separate compilation. Actually, I think, so this is main, yeah. Let's get rid of this one, and this one is probably going to be the new main. This is the new main, and main new is just the new main. We can get rid of that. So now, what I want to do coroutine O. Oh. And we're going to be compiling, so this one is just like main. We're going to be compiling coroutine C, but we're going to be compiling only the object when I do -c, right? So it's a partial compilation, so to speak. So I can even demonstrate to you how it's going to look like. So make O, and it didn't compile. Oh yeah, because it doesn't have size T. All right, so let's include, as far as I know, size T is defined in stdlib, right? So we'll need malloc anyway. I just realized that we never free. How do we free this shit? Bro. We can probably append the stack. Yeah, okay, so I'll have to think about that. So do we have a to-do for that? I just realized that we just leaked the memory. So do we have a to-do for that? Okay. So finish. So to do free this stack of finished coroutine. I'll have to think. So one of the idea I have is to have a second array of contexts, and upon deleting the coroutine, I append its stack base to that array, and when I'm reaching the main routine, I may periodically just flush them. You know what I'm talking about? So it's just like postpone their deletion and just maybe periodically, or maybe never, or maybe reuse them. I don't fucking know. So what's funny is that it is put at the end of the dynamic array. When we allocate a new routine, we can actually check if we have additional pre-allocated stuff, and maybe some of them contain already allocated stack. We may try to reuse that stack. That's a cool idea, honestly. We don't lose it. It's still on the dynamic array. It's just, it's behind the counter. We can detect that this is an allocated stack, and we can just reuse the same stack. So we don't have to, yeah, we can do something like that. That's a cool idea. But anyway, it's going to be to do. I don't want to think about memory management too much. All right. So something like that. So it's kind of an interesting idea. But anyway, what I was doing, I forgot. So yeah, it's my assert declaration. So we need to do an assert. So this is assert. All right. So that created an O. Okay. So I want to try to now build main. Right. So main wants to have context current. We can actually have something like, I don't know. So maybe coroutine ID, which returns the current. I kind of want to abstract away the access to this array of context, because I think it exposes too much. So let's create coroutine H, right? If not defined, coroutine H. So let's define and let's end diff like so. and the coroutine.c. So what does it want? We can just do something like coroutine ID, right? It doesn't really return anything. So this is a coroutine ID. In a coroutine ID, we're going to just return context current, contexts current. And when I'm trying to compile the whole thing, so it complains about that, so but we can say coroutine ID. Coroutine.h. All right, so coroutine yield. So that's another thing we need to have an h. Yield. Finally, can I just forward declare it like that? Is it still going to be naked? I think it's still going to be naked. Yeah, so it's like a naked implementation. All right. Coroutine init, understandable. Where is init? So here it is. Yeah. We don't need to even forward declare it, but I mean, it's fine. So this is init. What else? It wants to have go. Coroutine go. We're almost there, chat. We're almost there. We just need to move some declarations to H file and we're almost done. Count. Okay. So we can also forward the count, or now let's forward the count. Right. So coroutine alive. Right. So it's going to return how many of them are alive. But this ID may change. Oh yeah, that's true. The ID may change because. Yeah, so this ID, it's not uniquely identifies this thing. Yeah, we'll have to think about that. One of the things we can do, instead of like removing those things from the array, we can mark contexts as dead to preserve ID stable. Yeah, so, okay, this is another to-do that I probably want to look into at some point. So finish. By removing elements from the contexts array, we invalidate IDs. Right. So I suppose we're just marking them as dead, which makes it easier to actually then reuse the stacks. So then when we allocate a new context, instead of like appending it, we can just iterate, find the tombstone, right? So tombstone, and see if it has allocated stack, and just reuse the slot with that stack without reallocating it. Okay, so this is another thing that makes it easy. Okay, all right, that's pretty cool. But I'm gonna do that later, maybe off screen even. Right. So my goal right now is to make it work in C3, right? So because I need this kind of stuff in C3. So coroutine alive, and this is how many of them is going to be alive, right? So this is that, and this one is going to be size t, and it's not going to return anything. So coroutine, right? So and this one just returns contexts count, context count. Okay. Undefined coroutine ID. This is not true, mein Freund. What the fuck? This is because I never actually linked with this kind of stuff. All right. So I'm still. Are you shitting me? The fuck? Here it is. Am I okay? So maybe I have to do -b. Bro, what did I forget to do? So H file, I edited it to H file. So here it is in H file. In C file, here they are. I actually edit them, and so yeah, here they are. So here is that C file, H file. In main, I include coroutine H. Depend. Oh, freaking make files. God fucking damn it. Missing semicolon. Yeah, exactly. Yes. It's because of the missing semicolon. Right. So they're not optimized out. They're definitely not optimized out. Okay, so cool. And if I try to run this entire thing, yep, that's pretty cool. Okay, so let's do main C3. Let's do main C3. So module, and depending on how we call the module, it's going to depend how the executable is going to be generated, right? So let's say this is going to be main C3. Right, so in here, void main, like this, and if I try to do C3 compile, main C3, it generated main underscore C3. So the executable actually depends on the module name, right? So we can kind of control it through the module name. So let's actually put all of the coroutines to a separate module, right? So it's going to be module coroutine. So as far as now, you can refer to the C functions by a different name. So one of the things you can do, for instance, you can create a function init, and then you can say that the external name of the function is coroutine init. So that way, in here, when you import this thing, you can do something like this, right? So the name itself has a prefix, but in C3, you can actually turn module into that prefix, right? So this is the kind of stuff you can do, right? So now I can try to build, maybe I need to create like a make file, right? So let's do main C3, depends on main C3, and here we're gonna do C3C, compile main C3, and also the O file. There we go. Why did you do it like that? Okay. So let's do make. All right. This looks like beginning of the declaration, but it's missing a fan. Oh yeah, I forgot the fan. Just a second. Of course, obviously. Expected function body. If you want to declare, but I already said external in here. Is it not enough? Goofy language. Okay, so that seems to be working. All right. So let's actually define other functions, right? So coroutine routine.h. So we need yield. So that's easy. Yield. We need go. Right, so go is that, but we also accept a couple of arguments. So if I remember correctly, you can't really define function pointer like in C. You have to first redefine them. So let's say coroutine fn void. Right, so something like this. So and in here we accept you know, coroutine fn, which is f, and also arg. Right, so that's what we're doing here. So after that we also have to do id, right? So this is id, and this is use size, and in here we can do something like alive. All right, so that should be it. You know what I just thought about? Wouldn't it be cool if you also have to call finish at the end in here? But for the main routine, it is not going to work. Right, because finish, maybe it will work actually. I think it will work. Wait a second. So if I just do something like that, implicit declaration. Oh yeah, so we can explicitly declare that. Why not? For routine. So let's do finish. So, and that will just return the last element, right? Wouldn't it? I think it will. All right, so, and then I call main. Floating. So what does it do? Why does it exactly does it fail? Oh, because it tries to switch and shit. Yeah. So it tries to switch and shit. Yeah, so it tries to restore. Here's an interesting thing. We can do. If context current is equal to 0, about that. If the main coroutine finishes, it not only finishes itself, it finishes everything else. Like straight up. So it just like, you know, deinitializes the whole context and stuff like that. Reclaim all memory. Yeah, it would be also nice to reclaim all memory. Right. So, but I'm gonna do that later when I work on this specific to-do. So, yeah, that's kind of nice. So let me try to do that, and contexts, and that works. So that's pretty cool. So it kind of makes it nicer, I think. Right. So essentially, here you start the coroutine runtime. You do a bunch of coroutines and stuff like that, and you finish it, and the runtime is kind of like restored back to normal. Right, so init and finish. And it's kind of the same function. Yeah, that's kind of interesting. So, and then in C3, you can actually do something interesting. You can actually do something interesting. So finish, and you can use even defer. Can your C do that? I don't fucking think so. Anyway, so we need to define like a counter or whatnot. So counter. So here we're gonna accept the void arg, right? And let's just create a bunch of things. So coroutine go. So this is gonna be counter. Then I suppose we can do 20. And here, maybe 5, I don't know. So, yeah. And in here, we can just do something like n int arg for, but maybe I want to actually use size in here. So use size 0, n plus I, print fn. So this is going to be the coroutine ID I, and we should not forget to yield the coroutine. Okay, so I want to just like try to run the whole thing and see how it goes. Okay, so it has to be C3, honestly. C3. All right, so we don't have IO. Let's include IO. What else? So expected function followed or prefix. Really? Oh, you have to, it's, okay. Man, I hope it's not going to create like a pointer of pointer, right? In that case, it may create some problems. Void, yeah. So it has to be void star. All right, okay. It didn't crash or segfaulted or anything. So let's do coroutine yield, a single yield, and see. Okay, so that seems to be working. Can I now do the loop while coroutine alive greater than 1, just keep yielding. All right, so that's it. Okay, so it does in fact switch bit. Oh, okay, so you can have coroutines in C3 now. Oh shit, C3 website is not working for me, but yeah. So I guess I just edit you know, asynchronous programming to C3, even though it doesn't support it explicitly. I just say so forever loop in coroutine adaption when? Yeah, this is an interesting thing. So these coroutines are actually not resistant to one coroutine basically taking over all of the resources. Right, because you have to yield manually periodically. One way to actually combat that, I was thinking, is to put a yield into some sort of an interrupt. So as far as I know, in POSIX, there's a very interesting thing, like, I don't remember how it's called. I think it's something like a set timeout or whatever. I don't remember the function. Do you guys remember? So POSIX signal by timeout. What was the function? alarm, maybe alarm, but I'm not 100% sure. Set alarm clock, okay, to deliver a signal, could be. So there was also other functions. Timer create, I think timer create. Yeah, something like that. So yeah, and essentially you take your yield code, and put it into the interrupt handler. Then instead of calling yield manually in routines, you basically periodically do the interrupt. So, and that way you never have to yield explicitly. Just did we die? So or what's up with that? That's so cursed. Is it cursed? Okay. Is it really cursed? Because I feel like this is exactly what operating system doing. Isn't it what exactly operating system doing? It's more cursed than you can imagine. Well, I mean, I understand that it may create shit ton of problems because it may actually interrupt maybe in between instructions and shit like that. But well, you have one statement of the language, right? And one statement can be several instructions. It can interrupt in between them, and you kind of have to take that into account and shit. So, like, I understand that it's kind of dangerous, right? So, and because of that, I don't want to do that right now. So, as far as now, Golang handles with Signal 23 urgent. Right. I think it's more or less how early user space-based threading in Linux worked. Yeah, I think so. It looks like it. Before pthreads. Yeah, I don't want to implement this kind of stuff right now because I don't really need it, right? But I'm gonna keep it at the back of my hand, just in case, because it's kind of it would be kind of interesting to explore this kind of stuff. If you want preemptive multitasking, just use threads. Yeah, at that point, just use threads. So my goal is to make my WebSocket implementation asynchronous with the minimal amount of effort. Right. So without rewriting too much code. And I think using coroutines for that is an interesting approach to try at least. So, and since I already have coroutines, they even work with C3, so I can just like go ahead and use them. So let me go ahead and maybe commit everything. So I want to probably git ignore C3 as well here. Yeah. Okay. So yeah, re-implement coroutines entirely in GNU-C. Right, so because we do depend on GNU extensions and stuff like that. So I'm gonna push that right into the repo. So that should be already live for anyone who's interested. So here it is. So you can play with my coroutines, with my shiny coroutines. Custom coroutines implemented. Nah, we actually completely get rid of the, flat assembler, right? So in GNU-C. Well, what does it say? Okay, that's bizarre. So remove flat assembler from README. It's kind of sad, but it is what it is. I really like flat assembler, but if we can do it like that, it just like removes the amount of moving parts in the implementation. Right, so because you only need one compiler now. So, which is kind of cool. Even though I don't like GNU assembler, I think it increases the simplicity. I think so. Right, that's pretty cool. Man, it's kind of cool that this is the only low-level thing you need in here. Which means that, yeah, it's going to be easier to port that to other platforms. So the less surface, the contact surface area with actual CPU, the easier it is to then port to ARM, for instance. Because on ARM, you just need to implement these things. And there you go, you support ARM. So on another platform, you just implement these two things, and they're very simple. I'm pretty sure on all of these CPUs, it's going to be pretty much the same. It's just like the registers are going to be different, and instructions maybe going to be slightly different. So, and naked attribute seems to be widely supported. Okay, that's pretty cool. And even if we want to compile on something like MSVC, it's really easy to if-def all of that stuff, right? So it's a very small compiler and platform dependent part that is very much like easy to port. So I'm super happy with this implementation. Actually, I didn't expect it's going to be this good. All right. So I guess I achieved everything I wanted to achieve. So let me take a look at the subs. Hammer Banner, thank you so much for Twitch Prime. Knakius, I hope I pronounced your nickname correctly, thank you so much for Twitch Prime. Senkere the Sorcerer, I hope I pronounced your nickname correctly, thank you so much for 6 months of pure recreation. Thank you, thank you, thank you. Hector HSC, thank you so much for 100 beats. Felix, thank you so much for the Prime with the message. Hell yeah, brother. Okay, cool. Nayo S, thank you so much for Twitch Prime. All right, that's it for today. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Ahu. I missed it. I love you. Mwah.